All right, so this video is going to go through pages 6 through 8. We're going to go over the parts of a wave. So our first wave that we're looking at, first of all, this is a transverse wave, the one that looks like a typical wave. Okay, so make sure you know what a transverse wave looks like. Okay, first thing we're going to label on here is this middle dark black line. That is called your origin. Okay, or you can call it the equilibrium. Either one is fine. Okay, but that is your middle line that you're comparing the wave to. Okay, then you have the top of a wave that is called a crest. Okay, so a crest is the max displacement from the origin in the positive direction. That's all it is. It's just basically how far, it's basically as far as it goes in the upward direction. Okay, then you have the bottom part of a wave that's called a trough. Okay, always remember a trough, because if you look on a farm, a trough looks like this, where it's like basically a half of a cylinder, okay, that you dump food into. So that's why I remember that. Okay, however you need to. Okay, the trough is just a max displacement from the origin in the negative direction. Okay, so that's a crest and a trough. Now, when you have the height of a wave, either up or down, positive or negative, okay, these are called your amplitudes. Okay, so amplitude is just the height of a wave. So if I ask you to change the amplitude, you'd either make it higher or lower. Okay, and the amplitude is just a measure of distance from the origin. Okay, so how far it actually goes up or down, that's what your amplitude, or how you actually calculate your amplitude. Then you have your last thing is called a wavelength. A wavelength is one full wave. So as long as you start in the same spot, okay, that is a full wave. So this is characterized by lambda, that is an upside down y. Okay, so that is your wavelength. And it has to have one full crest, so one full up, and then one full trough, one full down. If it does not have both those, it doesn't count as a wave. So let's say I have started a wave. Let's just change the color real quick. Let's say I started a wave right here. Okay. The only time it'll be a full wavelength is if it has one full crest, one full trough. So it has to go all the way up. Okay, that would be half a wavelength right there, and it has to go all the way down and end in the same spot. Okay, so that would be one full wavelength. Okay, so as long as you have one full crest and one full trough. Okay, so a couple things we're going to talk about too that we're bringing back is period. Okay, so remember we talked about this in circular motion. Period is the time it takes for one rotation. Well, we're just going to basically say the same thing, but now we're going to deal with waves. It is the time for one full wave. Okay, so how long does it take for one full wave? And so we have an equation, remember the T equals 1 over F. Okay, then you had your frequency. Okay, so that was also part of circular motion. So frequency was just the number of waves in 1 second. So number of waves in 1 second. And that was F equals 1 over T. Okay, and so those are reciprocals of each other. Okay, basically meaning they're opposites. So period and frequency we'll worry about more when we actually start changing up some waves and actually doing calculations here in a little bit. Then you have this wave right here. This is a longitudinal wave. So a longitudinal wave is just, so it's not a transverse where you have particles going up and down like this. Basically all you do is you have particles that are just being compressed and stretched from side to side or up and down. It doesn't have to just be horizontal. Okay, but there's a couple things we need to learn here is the area where it's nice and compact, that is called a compression. Okay, so that one's not too hard because that one's pretty easy to understand what that word means. Now, a new word that we did learn, remember, is a rarefaction. A rarefaction is basically the term for being stretched out, when it's stretched out the most. Okay, so make sure if you're going to have trouble with that word, make sure you star it. Okay, and then you're good to go. Okay, now to have a full wavelength in a longitudinal wave, you have to have one full compression and one full rarefaction. So if you started like here, right in the middle of that compression, and you went to the middle of that next compression, that'd be good. Or if you started in the middle of a rarefaction and went all the way to another rarefaction, that'd be a wavelength. Okay, or if you started at the beginning of a compression and went all the way to the end of a rarefaction, okay, because you have one full compression, one rarefaction, that'd be a wavelength as well. Okay, moving on to the next page. So which is a transverse wave and a longitudinal wave? Label them. So This is going to be our transverse wave right here because it looks like our typical wave. And this right here where you have light and dark areas, that is where things are compressing and stretching. So this is a longitudinal wave right here. On the longitudinal wave, label a compression and rarefaction. So a compression is when everything's real dense. That's when it's going to get darker. Okay, so that is a compression right here because everything's brought together real closely. And if it's lighter, that means everything's nice and stretched out. So that would be a rarefaction. Okay, 3, what is a wavelength? What is one wavelength equal to in a transverse wave and longitudinal wave? Okay, so wavelength is just one full wave. Okay, that's nothing too crazy there, so one full wave. Now, on a transverse wave, you have to have one full crest and one full trough. Okay, on a longitudinal wave, you have to have one full compression and one full rarefaction. Okay, so that is what determines a wavelength on a transverse or longitudinal. As long as you have one of each, okay, whether a crest and a trough or a compression or rarefaction, you're good there. How many cycles or vibrations are there in one wavelength? So a vibration is technically a wave, so it only takes one cycle or one vibration to be one wavelength. So just one, that's it. What is the amplitude of a wave? So remember, that is your displacement from the origin to the crest or the trough. So it doesn't matter if you go up or down, they're both the same. Okay, so that would be the amplitude. Frequency, what is the frequency of a wave? That is just the number of waves in 1 second. Okay, moving on, next page was the period of a wave. That is the time for one full wave. What is the relationship between the period and the frequency? So those are going to be reciprocals of each other. Okay, so that is just, their equations are basically opposite, so they're just reciprocal, so nothing too crazy there. Draw a transverse wave, label the amplitude, wavelength, crest, and trough. So remember, your transverse wave just looks like this, nice flowing wave. Okay, your drawings don't have to be perfect as long as we get the gist of it. So amplitude is going to be your distance from the origin to the top of the crest or the trough. So either one of these is going to be your amplitude. Okay, a crest is going to be the top of a wave, so a crest could be up here, and then your trough is going to be the bottom of the wave. Okay, and your wavelength, as long as you have one full crest and one full trough, you're good. So you could start here and then end here. That'd be wavelength. You could start at the top of a crest and end at the other top of the crest, you're good. Or start at the bottom of a trough, end at the other bottom of a trough, and that would be wavelength as well. As long as you have one full crest and one full trough. And that will end that one.